Welcome everyone. My name is Ivan and I'll be presenting the paper Security in Asynchronous Interactive Systems, which was written jointly with Joe Halpern from Cornell University. Let's begin. Mediators often make solving problems much easier. In fact, many interactions in our daily life require a mediator, as for instance, elections, lotteries, internet applications in which we have to communicate with an internet server, and even exams or college admissions. In all of these situations, it is critical that the mediator is trustworthy and that it follows exactly what is intended to do. Otherwise, it could subvert the whole purpose of each of these examples. This raises a natural question, which is if we can simulate all of these interactions without the need of a mediator. However, what exactly does it mean to simulate? Let's look at the election example. We can trivially implement this interaction by having each agent to send its vote to everyone else, and then for each agent as well to count the votes locally and compute the winner. We can see that if everyone follows the protocol, then we get the same output as if the mediator performed the count. However, this protocol has some issues. First of all, agents may disagree on the winner. If I tell the first agent that I vote for candidate A, I tell the second agent that I'm voting for candidate B, then it might end up that the first agent believes that A won in the end, while the second agent believes that B won. Moreover, with this scheme, agents learn the vote of others. Votes here are public. And therefore, it happens that agents may also condition their own vote on the vote of others. For instance, if I see that my preferred candidate has no chance of winning, I might vote for my second preferred candidate instead. This example suggests that we might need a stronger notion for simulation. In fact, the traditional approach is to require that the simulation is at least as secure as the original protocol, in the sense that every outcome and basically everything that could happen in the protocol without a mediator and some adversary could already occur in the protocol with the mediator and the same adversary. In our model, an adversary, it controls a subset of the agents, and since we're also in an asynchronous system, controls as well the order in which the agents are activated and when the messages get to each of the recipients. Under this model, a result that follows from Ben Orr-Canetti and Goldrich's work shows that all asynchronous protocols for n agents and a mediator can be simulated by a protocol without a mediator whenever the number of agents is larger than 4 times the size of the adversary. Note that Ben Orr-Canetti and Goldrich's result talk about multi-party secure computation. However, if we only require one-way simulation, we can easily reduce it to a single instance of multi-party secure computation, and the result follows. Going back to the definition of simulation, note that it tries to capture the idea that no matter what happens, no matter what the outcome is in the protocol without a mediator, since it could already happen in the protocol with a mediator and we could get the same thing, it is not worse. So basically, the worst case scenario without a mediator is no worse than the worst case scenario with a mediator. And in that way, this new protocol is considered secure. However, what happens when we look beyond this worst case scenario? Let's take a look at the following 2 examples. In the first one, suppose that n agents want to decide who has the fastest internet connection. They decide to perform a latency test. Each agent first sends a signal to a given mediator, which is just a designated server in the internet. And then the server waits until it receives a message and sends the ID of the agent whose message got first to all agents. This is a pretty standard latency test. However, it turns out that under the definition that we gave in the previous slide, a protocol in which all agents do nothing and simply output 1 simulates the protocol above. What does this mean? It means that a protocol in which agents perform no test whatsoever and decide unanimously that the first agent has the fastest internet is simulating a latency test. And why is this? Well, know that we already are requiring that every outcome that could occur without a mediator could also occur with a mediator. Suppose that we have any adversary in this protocol where agents output 1. Then we have that all honest agents are outputting 1, while the adversary might output whatever. And in the protocol with a mediator, we can have the same adversary that outputs the same thing, while it ensures that the message from the first player gets first to the mediator. That way, all the honest agents would output 1 as well. Note that if the first agent is honest, it will always send a message, and if the first agent is not honest, is part of the adversary can always send a message because it controls it. Therefore, this shows that basically this protocol that has nothing to do with a latency test is simulating it according to our definition. In our second example, we have that n congressmen are voting to pass a bill that requires 90% of support. Each agent, in this case, sends a vote to a trusted mediator who performs the count and sends the result of this voting process to all congressmen. If we want the protocol to tolerate adversaries of size up to a fourth of the total number of congressmen, then the mediator cannot wait until all congressmen report their vote, since it may happen that 1/4 of the total congressmen do not report theirs. Thus, the mediator can wait only up to 3/4 of the total number of congressmen to report, and then it might leave some time, but it has to close the voting at some point and report the results. Therefore, a very similar argument as the one given in the previous example shows that a protocol in which all congressmen do nothing and just reject the bill simulates a protocol above for adversaries of size n/4, where n is the total number of congressmen. Again, why is this? What happens is that in the protocol with a mediator, regardless of how the congressmen vote, the adversary can just delay 1/4 of the total congressmen so that their votes are never taken into account, therefore making all the other congressmen reject the bill. So since rejecting is always a possibility in the protocol with a mediator, then we might just reject it beforehand in the protocol without a mediator. However, this protocol is not even given the chance for the bill to pass. These two examples suggest that we might want a stronger relationship between the protocol with the mediator and the protocol without the mediator than the one that one-way simulation is providing. For this purpose, we introduce the concept of bi-simulation, in which we're not only requiring that all possible outcomes without a mediator could occur as well with the mediator, but also the other way around. So we also want that all the outcomes that could occur with a mediator are also possible without the mediator. Note that with this last requirement, it rules out the protocols that we provided for the previous two examples. For instance, in the latency test with the mediator, there are cases in which the first agent is not selected as the fastest one. And in the case with the voting with the congressmen, there are cases in which most of the congressmen are honest and submit their votes in time, with the permission, of course, of the scheduler. Therefore, as we can see, it circumvents some of the issues that we presented so far. Let's take a look at what this definition says more precisely. It says that for every adversary A' in the protocol without a mediator, there exists an adversary A that controls exactly the same agents in the protocol with the mediator, such that when running these protocols with A' and A respectively, they produce exactly the same distribution of outcomes for all possible inputs X. Note that this notation here, exec pi a x, just means the distribution of outputs whenever we're running this protocol pi with adversary A and input X. The next bullet of the definition is requiring the converse of what we just said, which means that for every adversary A in the protocol with the mediator, there exists an adversary A' in the protocol without a mediator that controls exactly the same agents, and that when running these protocols with A and A', it produces exactly the same distribution of outcomes for all inputs X. We also use the term T by simulation when these properties are satisfied, but only for adversaries up to size T. Our main contribution in this paper is showing that all asynchronous protocols for n agents and a mediator can not only be simulated, but also bi-simulated by a protocol without a mediator whenever n is larger than 4 times the size of the adversary. Moreover, we show that the protocol that we provide satisfies additional security properties even when the size of the adversary can get up to 1/3 of the total number of agents. More precisely, suppose that we have integers m and m' such that m is larger or equal than m' and the total number of agents n is larger than 3 times m plus m'. Then the protocol that we provide satisfies that if the size of the adversary is less or equal than m', then it satisfies all the properties of bisimulation with respect of the protocol with the mediator. Moreover, if the size of the adversary is less or equal than m, and possibly larger than m', then it satisfies the properties of relaxed simulation instead, which is defined exactly the same way as by simulation. However, we consider in this case that the adversaries are not constrained to deliver the messages eventually. So adversaries can basically keep the messages forever and never deliver them. Intuitively, the whole point of relaxed by simulation is that the damage done by the adversary is not irreversible, since it can always decide to deliver all these missing messages, and all the agents can continue the computations when they left off and compute and terminate the protocol with no errors. To see why this result is an improvement over the previous result, suppose for instance that we have 12 agents. Our result says that we can always bisimulate any protocol with a mediator with 12 agents whenever the adversary size is less or equal than 2, since the total number of agents has to be more than 4 times the size of the adversary. However, since 12 is larger than 3 times 3 plus 2, we can set m to 3 and m prime to 2. And what it's saying is that, okay, we can construct a protocol that not only bisimulates the protocol with a mediator whenever the size of the adversary is less or equal than 2, but whenever the size of the adversary is less or equal than 3, it has these properties of relaxed bisimulation. If we set m prime to 0, we get the corollary that we can always relax bisimulate a protocol whenever the total number of agents is greater than 3 times the size of the adversary instead of 4. Moreover, in any of these cases, if we allow a small probability of error, it is only required that n is larger than 2m plus m prime instead of 3m plus m prime as originally. The next slides are going to describe the high-level construction of this protocol that we provide. Intuitively, agents simulate the protocol with the mediator as follows. Each agent gives a piece of the mediator state, and they use sequential instances of multi-party secure computation to update the state with new messages and to compute the messages that the mediator would send to the players. The inputs of these instances of secure computation are precisely the messages that the agents would send to the mediator in this simulation. Moreover, on top of this, agents send a special kind of signal that determine which of the agents or the mediator are supposed to be scheduled in the simulation. The real scheduler then can influence the computation by delaying these signals in the same way that it could influence the computation in the protocol with the mediator. That way we guarantee that all the outcomes that we can get in one of the scenarios are also possible in the other scenario, even when the protocol is highly sensitive to scheduling and to the delivery time of the messages. We can show, of course, there's a lot of subtleties, that the resulting protocol then simulates the protocol with the mediator whenever the number of agents is larger than 4 times the size of the adversary. However, the full proof of correctness uses the fact that the adversary in the protocol with a mediator can simulate its counterpart in the protocol without a mediator, and vice versa, all with no rewinds. Where no rewinds means that the adversary cannot try to do some stuff, then see how the agents react, and then go back in time and try something different. As follows from the result from Kuzinlevich, Lindell, and Rabin, it means that this protocol that we're providing is also secure in the universal composability model, which means that if the protocol without a mediator is used in some subroutine of some larger protocol, it can be substituted by the protocol with the mediator while preserving all its security properties, and vice versa, which means that if we have the protocol with the mediator as a subroutine of some larger protocol, it can be substituted by the protocol that we're implementing while preserving all the security properties as well. In conclusion, we've shown that one-way simulation has some limitations, and we introduced the concept of bisimulation to deal with some of these issues. So the limitations are especially highlighted when the protocol is highly susceptible to the scheduling of both agents and messages. We also show that any protocol with a mediator can be perfectly bisimulated in asynchronous systems whenever the total number of agents is larger than 4 times the size of the adversary. Moreover, if we're willing to sacrifice termination with these enhanced adversaries that do not deliver messages, we can tolerate up to deviations from up to 1/3 of the agents instead. And finally, the resulting protocol has universally composable security. As future work, the main question is if we can extend our results to a security model with a tighter connection between the real and ideal executions. For instance, if we assume that the scheduler is independent of the adversary, as like in internet lag, where the lag can be random or localized, can we construct a protocol such that for all schedulers, all inputs, and all bounded collision of agents, we get the same distribution of outcomes with and without a mediator? Also, in all of our results, even those that allow a small probability of error, we're not assuming the existence of one-way functions or any other cryptographic assumption. Can we get better results or better bounds under these assumptions? We hope to provide answers to these questions in the near future. Thank you very much for your time, and I hope that you enjoyed the talk.